Can you hear me on YouTube? Yeah. The main issue is everyone will overestimate themselves, isn't it? Hmm? If she want to leave that one, why she came in the first place? Hmm? Did you ask? No? Okay, let it be. Isn't it? I mean, overestimation means, suppose today I will do what you call 10 MCQ, I will design 10 MCQs. It is overestimation. I can't design 10 MCQ. 2 to 3 MCQ I can design because I need to get ready for evening class, isn't it? That practicality is required. Whether I can do or not. Or if once we commit for that one, again, we should do it. So, this is the situation in our whole country, actually. Again, people say something they don't do. Okay. But when you go to England and US, okay, the civilization is developed in such a way that they don't what you call tell like that. Okay, I have seen. I mean, even at least one or two guys. I should have some example. Am I right? I mean, who is uh, uh, who is like us? Okay, they're not like us. The civilization is quite different there. I mean, maybe culturally we may not like them. Okay, but they don't do like that. Okay, that's why they don't need coaching also, isn't it? By the time they what you call go to graduation, they will do themselves. I mean, they will have that level of commitment. Okay, I was trying to extend this whole coaching to what you call abroad, because I'm solving all standard textbooks. They also need that one. There again, I didn't get much response because there people what you call sit and study actually. And one more thing is again, 2 to 3 people joined. I mean, they have done actually, and one of the student is doing from US. I mean, they are saying I will study 1.5 hour per day. They will definitely study 1.5 hour per day. They will not say I will study 10 hour per day and doing nothing. Is that okay? Pick up. Like that. I mean, you should what you call one. I mean, you should target big, but you should commit to your words, isn't it? Yeah, I mean, if you escape from one circumstance, you will definitely escape everywhere, isn't it? Speak up. Again, nowhere it is easy. Am I right? Speak up. I mean, if you escape from learning, what will happen is you will end up with some other job other than physics, or some small job related to physics. Somewhere you can be what you call happy with teaching. Teaching is good, but not what you call highly paid teacher. You will never become highly paid teacher. Is that okay? Speaker. That also in the teaching field also, if you work hard, then only you can earn lakhs, 2 lakhs, 3 lakhs per month. Okay, that's not a big deal. But you should not escape from learning. You should not escape from hard work, isn't it? There also, isn't it? If you escape from here, you will escape everywhere, or you will what you call how to say escape from hard work. Then you will deserve whatever you you are capable of. Are you getting fine? I mean, you may end up with a teaching where 15,000 per month will be paid. Is that okay? They will not raise the salary. You will stuck there. Are you getting fine? So that's why again you can't avoid learning. Okay, in this 21st century age, okay, in any field you can't avoid learning. So that was our parents' age. Once you learn, again throughout your life, you can deal again. You can deal with whatever you have learned, isn't it? That was our parents' age, isn't it? Even in the corporate field, you check out, okay. Even in the engineering field, okay. If they learn daily, or if they learn and what you call solve some problem or some problem, I mean not this problem, physics problem, okay. Then they are highly paid. What you call suppose techies and all. Is that okay? So they will be paid 3 lakh, 4 lakh, 5 lakh, okay, maybe crores of rupees by Google and all, isn't it? So, but that attitude is important, okay? You can't avoid learning, okay? Whatever the field you go, you can escape from here, but you can't avoid learning, okay? So that's why, so I'm expecting quite commitment here. You finish this. I mean, there was a student, okay, well, in my first or second batch, in the beginning she couldn't do even LCM or something. Okay, in north part of Karnataka we have some problem. Okay, I think many foundations are working on that. When we again high school and college class plus two education is very poor. So because of that, again, I mean, there were many students who couldn't do very simple problem. Okay, uh, around 6 students were there, as I remember, 5 to 6 students. I used to take them separate classes to teach some small integration, trigonometry, and all. Okay, only one student show commitment. Okay, I mean, they couldn't do LCM. Okay, I mean, high school level again, article, very basic mathematics. Okay, so, but at the end, again, she could able to do CSIR level problem. She couldn't crack exams because, again, from what level to what level, isn't it? But she could able to do those problems. I mean, at least she could able to understand those problems. Now she is a teacher there. Okay, she is what do you call, earning her respect. I don't know how much money she is earning. She is definitely earning her respect. But again, out of 5, only one student shown the commitment, and other student escaped actually. And they are teacher now. Those who escaped, they are teacher again in the north part of Karnataka. Again, they will run out next generation. But one teacher in his life, how many students they need to guide, isn't it? Speak up. If you are a escapist, then you don't go for teaching. Okay, speak up. You will definitely ruin students' life. Okay, daily you need to update. You should be able to sit and study. That's it. Okay, I mean, or you should be able to learn somehow. Suppose if you can't sit and study, you have video lectures, you have MIT course, you have NPTEL course, isn't it? You have a lot of stuff again in this. I mean, you should be able to sit and learn and apply. Is that okay? If you don't have that attitude, you will definitely keep on escaping. You will end up with a job just like, again, you can go to do a bank job, isn't it? Bank, even in the bank, clerical position, not officer position, because there you need to take decisions. Am I right? Speak up. You can do those jobs. Are you getting the point? If you don't develop that attitude or quality, you better to do those jobs, or better to stick for that kind of job. Why do you struggle with the life, isn't it? If you are happy with those things, if I don't want to learn, then again you can go to but in 21st century, whatever the job you have, look at here, my assistant, am I right? So again, initially he didn't learn anything. It killed a lot of my time. Okay, then I spoke to him, you should develop some skills. Okay, now he can type anything on LaTeX. I have designed around 10 questions. Okay, now I will give it to him. He will type in LaTeX. He will give it to me. I'll just article. Just check that out. Look at here. Again, even my assistant. Okay, I mean, he needs skill. I mean, all jobs need skills now. Okay, not only skill, he need to update himself. Now I'm asking him to learn some communication skills because he need to speak to the student whoever call. He need to explain about our course, isn't it? And next thing is he need to learn this digital marketing, the very booming field in this what you call age, isn't it? So again, he's learning those things. Okay, I mean, even one assistant job, okay, it's not teaching assistant. Are you getting it? Technical assistant, small technical assistant, that requires learning. If he's not learning, I mean, I would have told him, you go and find other job. Is that okay? Speak up. This much small job in this 21st century requires learning and updating and developing skills. Okay. In again, forget about teaching. Teaching requires a lot of learning, a lot of upgradation. That okay. Then only you can what you call give justice to that particular job. And any job in this century, okay, you don't think again, if I crack CSIR net, if I become assistant professor, it is over. Are you getting point? If you think like that, you are going to ruin what you call thousands of students' life. Are you getting point? Speak up. Or if you think after PhD, my what you call my learning is over, I don't have to sit and study again. I can be happy. Hmm? No, I mean that's not the attitude. Is that okay? The main problem with this generation, it actually, again, you guys, if you don't know Kannada, you should what you call, learn Kannada because we have very good literature in Kannada. You know, after Hindi, the next highest Jnanapita prize, you know. Again, you are all Kannada, isn't it? Jnanapita, you know, Jnanapita prize is the highest award for literature, I think. Okay, in India. Hmm? For Hindi, we have 11 Jnanapita. Okay, Kannada, we have 8 Jnanapita. There are many states who speak Hindi, isn't it? Definitely, many literature will be there, isn't it? But Kannada is next to Hindi. Only one state. Hmm? Even in the border district, they don't speak Kannada. Are you getting my point? So literature is very good in Kannada. You can. It is worth learning Kannada to what you call read the literature. Okay. One of the what you call uh, one of the literaturists said, I mean, I don't know whether that word exists or not. Okay, speak up. I'm also from Kannada medium. Uh, he said that the main problem with this generation is they want to what you call earn without what you call doing work. That kind of mindset is developing actually. Hmm? I want to sit and make money. This is the mindset actually. Are you getting fine? So that is very, very wrong mindset. We are moving in a very wrong way. Is that okay? You can just see anyone, okay? They don't want to work and then earn, okay? They want to earn without doing much work, without struggling much work, okay? That mindset is quite harmful, okay? Pick up. I mean, you should, in any case, even if you are earning crores of rupees, in any case, you should have a mindset of working at least 7 to 8 hours per day. Are you getting point? Again, Ambani, Adanis, they won't sit and eat. Are you getting point? They work. Okay, they have that mindset. That's why they went there. Am I right? Or Tata or something. Okay, I mean they can sit and eat, isn't it? Speak up. What we would think again, low class people. If I have money, I will sit and eat, isn't it? I'll not do anything. So, but look at them. Okay, they are earning maybe in millions, isn't it? But still, they work so hard. So they may work more than 10 hours, isn't it? More than 10 hours, or maybe, I don't know. So, like that, I mean, we should have that kind of mindset, okay? I mean, not sitting and just eating, okay? That mindset should go, one thing. And other one is other literature, I mean, uh, I don't know. I mean, he was a professor, I think. He said, I mean, that is related to teaching, apart from that, okay? So, again, you should not, what you call, keep any of your notes while teaching, okay? Speak up. You have to make notes for each and every class, but you have to throw that notes after the class. You might have seen many professors, okay, who will teach the notes, whatever they have written around 10 years ago, 20 years ago, or 30 years ago, isn't it? I mean, they will not update themselves. They will not teach again, they will not touch again the same basic. Okay, basics are the same. The what you call the application developed, am I right? Speak up. I mean, they can touch it to application. That would be very great actually. But again, many of the teacher, okay, I mean, they will be saturated. They will teach whatever they taught around 10 years ago, 20 years ago. I mean, they will have the notes or something, whatever they know. So one of the poet, he said, I mean, he was a professor, okay, in Qatar. He said that soon after the class, you should throw off your notes to dustbin. Next class, you need to prepare again. I mean, you will have books and all, isn't it? You will have resources, you know where to study, isn't it? Next class, you have to study it again. So again, that is the way that again professor should be in my idea. Okay, in my idea. Is that okay? If you teach the same thing in the next next year only, I mean, you are not giving the justice to that particular what you call job. Is that okay? So in my idea, assistant professor should be appointed in such a way that those students who should able to learn and what you call at that suppose again if I want to recruit any teachers here, okay, if in future if I need any teachers, okay, I will give you 1 hour, I'll give you books, okay, you learn this concept and teach here new concept whatever you don't know, or I will ask you, okay, I will find out what concept you don't know, okay, yeah, so okay, you don't know this one, I will give you 1 hour or I'll give you half a day, you learn and teach me. If you have that quality, you come in. Is that okay? Whatever you know earlier, if you want to manage with that one, you don't go for teaching. Is that okay? Speak up. Daily. Again, even whatever I know, that is not what you call up to the mark. I mean, because of that, because of this mindset only, I'm growing. I'm learning. I'm reading new textbook. Okay, I'm expanding my syllabus, but the time restriction. Okay, again, only 6 months, isn't it? How much syllabus I can fit into, isn't it? Yeah. Now forget about everything. Now we shall move on to again. Let me recall what was our quantization integral 1 by h bar integral x1 to x2. X1 is you can say lower classical turning point. X2 is upper classical turning point. The region between x1 and x2 is classically allowed region, bound state. Okay, bound state. P of x dx, speak up. Plus phi 1 is a phase factor for x1. Okay, plus phi 2 phase factor for x2, that's equal to n into pi. I did lot of gimmick here, okay? I mean, while dealing with this one, I should have taken pi by 4 actually, while writing connection formula, because connection formulas are derived for smooth walls, not for rigid walls, okay? But I took pi 1, pi 2 or something, then I made some gimmick. Is that okay? I should put pi by 4 there in the article that IRE function or something, that pi by 4 will come. But I want to make a generalized quantization rule. That's why I made it up like this. Is that okay? Where this pi I, so that's equal to pi by 4 if xi is smooth wall. Okay, that's equal to 0 if xi is rigid wall. It actually pi by 4 comes after your connection formula and all. I'm going to, what you call, you better edit the last equation, okay? I mean, you better keep the pi by 4 while doing that one. Then you edit pi 1, pi 2 here, okay? So I think the book named by Devanathan, okay, there again, I think this is clearly mentioned. Any idea, anyone? Quantum mechanics by Devanathan. Many concepts are given very nicely there. Yeah, it is there, okay? It is there. Currently unavailable. Okay, what to do? Okay, it is there, okay? Let me have that copy. Because, I mean, there are many Indian author textbooks, okay, which which contain their what you call life experience actually. I mean, they taught 20 year, 30 year. Again, this is one of the textbooks. I mean, uh, Ishwar Singh Tyagi, okay, quantum mechanics. I'm not giving this textbook because here he solved problem and he gave what you call solution also. I mean, he gave problem, he gave solution also. Is that okay? Speak up. That's not good actually. But again, that book contains what you call his own stuff actually. Not everything, because something which quantum mechanics develop, they will present in the same way as other book. Okay, so many concepts are very of his own, and especially again at the end he's touching it to quantum computation or something. I think quantum circuits or something. That's very good actually. So like that again, this Devanathan book, I don't know, but again I have studied this part there. It was very clear over there. Okay, and these ideas and all. And not only this one, I think relativistic quantum mechanics is also given very well. Okay, in the same textbook. Just check that out. Okay, I mean if you are accessible to any library, if any one of you going to college, just check the textbook. Okay. Yeah. Is that okay? Rigid one. And you can apply this one. Okay, what is P of x? P of x is equal to momentum defined in a classically allowed region, 2m e minus v of x. If suppose v of x is specified, you can find energy eigenvalues without solving Schrodinger equation, isn't it? Speak up. That was the idea. Now look at here. Now again, I have given one problem which is half harmonic oscillator. Am I right? Pick up. Half m omega square x square here, infinity here, isn't it? Pick up as a function of x. So like that, again, I can give you one more problem. As we have solved this one, v of x is equal to some k into x when x is greater than 0. Okay, sorry, when x is greater than 0, that's equal to infinity when x is less than 0. I mean, half one side rigid wall. Can I say like this problem with one side rigid wall, other side smooth wall? If you take any energy here, okay, other side smooth wall. Is that okay? So by equating half m square x squared to energy, you can find this point. Am I right? By equating energy to this kf, you can find this point. Isn't it? One of the turning point is this one. Okay. This problem should be solved. Okay. This problem should be solved. So I mean, if you have potential like this, are you okay on Google Meet? Speak up. Yeah. If you have problem like this, v of x is equal to alpha mod x to the power v. V is equal to 1, 2, 3, and speak up. So when v is equal to 1, what is the potential? That's equal to alpha mod x. What is this one? Mod x curve. This also allows bound state. Speak up. This also allows bound state. What is v is equal to again when v is equal to 2 alpha mod x square is same as alpha x square. Am I right? That is same as harmonic oscillator. Pick up. If you write alpha mod x to the whole cube, if you write alpha mod x to the cube, you better write mod x to the cube. X cube is different from mod x cube. X square is same as mod x square, isn't it? Pick up. Anyway, it is positive. Mod x cube is it may be a little bit wider. Okay. It may be like this. Just check that out. Is that okay? Speak up. If you have this kind of potential, which is symmetric, okay, which is symmetric, and which allows bound state, only bound state. This allows only bound state. Am I right? Speak up. Now, again, you do it here. Okay, you do the problem for this one, harmonic oscillator. Okay, speak up. You better to once do the problem for this one. Okay, alpha mod x. But you don't have to do the problem for this kind of thing. You can work out the generalized what you call quantization condition. Speak up. That is given as one of the problem in Griffiths. I'll not do the problem. Okay, I'll just get the last answer. Are you getting the point? It should be symmetric. Okay, it should be symmetric. What you call potential, which allows bound state. Okay, in that case, look at here. We can work out the generalized formula. Okay, is that okay? Are you getting my point? What kind of potential that I'm talking about? So you better to work out one of this one. Okay, this is we already worked out yesterday. Am I right? It answer is already known. In case of half m omega square, I have alpha here. That's it. Is that okay? Answer is already known. Okay, in this case, look at here. How do you find these points? Equate E to alpha into mod x. Okay, that means mod x is equal to E by alpha. What do you mean by x then? Plus or minus E by alpha. If mod x equal to E by alpha, x is equal to plus or minus. X can be either positive E by alpha or negative E by alpha. Mod x equal to E by alpha, isn't it? So minus E by alpha plus E by alpha. Are you getting a point? How to find these points? Okay, speak up. For this kind of potential, which is symmetric, okay, which allows bound state, okay, or alpha x power v. Okay, I'll just write it here. V of x is equal to alpha mod x power v. V is equal to 1, 2, 3, and so on. Is that okay? V is equal to 1, 2, 3, and so on. Your energy, quantized energy, that's equal to, look at here, we need to manipulate this one, okay? We need to manipulate. Alpha into n minus half, okay? I'll just write whatever he has written first, okay? H bar root of pi by 2m alpha, okay? Gamma of 1 by v plus 3 by 2, gamma of 1 by v plus 1. Wait a second, whole power 2v by v plus 2. 2v by v plus 2. Whole power 2v by v plus 2. Is that okay? Now, I don't need in this format actually. You can keep it in this format. Now again, you know the answer for this one, isn't it? So what is the nth energy? Pick up En is equal to n plus half h bar omega. But here you have alpha, you don't have omega. Okay, you put alpha is equal to half m omega square, half m omega square x square. Am I right? Pick up. I want to write my nth energy in terms of alpha. I will just compare alpha to half m omega square. Then omega square is equal to, speak up, 2 alpha by m. Omega is equal to under root of 2 alpha by m. You substitute this omega, h bar under root of 2 alpha by m. Okay, pick up. This is the nth energy for this potential. Is that okay? Pick up. Since I already knew that n plus of h bar omega, I grabbed omega term from that one. Okay, m is the mass of the particle. Okay, speak up. Omega is a characteristic of that spring mass problem, root of k by m, isn't it? Mass is mass of the particle. Okay, omega is a characteristic of that potential, actually, potential curve, isn't it? Mass also decides, but usually mass will be mentioned in the problem. Am I right? Speak up. They will say particle of mass m moving in this kind of potential. Speak up. You should be able to write harmonic oscillator answer. Okay, then you should be able to convert that answer in terms of this alpha and mass of the particle. So can you do this kind of manipulation? That is required in many cases. Am I right? In many earlier problem also we did this one. I don't know whether you remember or not, isn't it? They have given some Gaussian wave function. They asked what is the potential correspond to that. We compared it with ground state of harmonic oscillator and we grabbed the answer. Isn't it? Speaker. No. What I'm saying is, if suppose this were half m omega square x square, my energy would be n plus half h bar omega, isn't it? If this potential were half m omega square x square, my energy would be this one. Now, in place of half m omega square, I have alpha. H bar is universal constant. What is the term extra? What I defined, that is omega. Am I right? You just equate half m omega square to alpha. Okay, you grab omega out of it, place that omega. That okay, that's it. That's what I'm saying. If this potential were half m omega square x square, energy would be this one. If potential is alpha x square, what is the energy? That is the question. Is that okay? I'm just comparing this coefficient and grabbing omega. M is the mass of the particle that will be mentioned in the problem. Is that okay? Pick up. Now look at here. Now you just check whether you get this one here or not. Wait a second. N minus half. Again, N minus half is there. Here we have N plus half. Whether N runs from 0 or 1 here. Okay, N runs from N equal to 1, 2, 3 here. In Griffiths, okay? The small n runs from 1 to 3. Okay, speak up. But here n runs from, speak up. 0, 1, 2. Is that okay? Speak up. So that's why what you need to do is, in place of this n, which runs from 1 to 3, you should place n plus 1, which runs from 0. Then you will get n plus half only. Are you fine? Speak up. Just check that out. I mean, you know gamma integral, am I right? Because you can work it out. Just apply it for what you call harmonic oscillator. When you apply it, you will remember the formula. Is it okay? But I don't need formula in this format. When I see exam question, I need it in a little bit different format. Okay, I need alpha power something. Okay, n minus half power something, and rest of the factors are constants. I need what you call my terms like this. Okay, so here alpha power 1, am I right? Speak up. 1 by root alpha power 2v by v plus 2. 1 by root alpha power, or alpha raised to half power 2v by v plus 2. Isn't it? Alpha power 1, okay? 1 by alpha power v by v plus 2. Okay? This is equal to alpha power 1 minus v by v plus 2. What is this one? V plus 2 minus v. Alpha power 2 by v plus 2. Is that okay? Alpha power 2 by v plus 2. n minus half power 2v by v plus 2. 2v by v plus 2. Okay, what is the rest of the factor? I'll take h bar root of pi by 2m gamma of 1 by v plus 3 by 2. Is that okay? Divided by gamma of 1 by v here. Okay, 1 by v plus 1. These are the constant raised to 2v by v plus 2. I want you to remember this one. Even this generalized problem is also asked in one of the just exam. Okay, it's a generalized problem, right? Is that okay? Now again, you don't forget that n starts with 1. But unfortunately, in exam problem, they haven't taken care of this n actually. But it doesn't matter to choose the appropriate option. Is that okay? Speak up. All options will be similar. Okay, you will not have confusion of n minus half, n plus half. I remember in the option they will give the confusion in the power. Then you choose the appropriate option. Okay, but the question that I have designed, I have taken care of this n. N will start from 1 here. Okay, if you want to start n with 0, you place in place of old n, you place n plus 1, then it will become n plus half. Is that okay? Speak up. Replace n with n plus 1 if n is equal to 0, 1, 2, and so on. Is that okay? Are you getting the point? Simple. So that's why you don't have to solve all problem. Okay, you can apply this one and get the answer. Okay, but one side rigid wall, other side smooth wall, you need to solve. There are no tricks for that. Okay, this is both sides smooth wall problem. Okay, and symmetric potential problem. Symmetric potential problem. Now he has given now again as a homework, apply this one. Apply this to linear harmonic oscillator. Is that okay? Speak up and evaluate all of these steps. Okay. Speak up. I think this pi is not there. Am I right? You have n plus of h bar omega only, isn't it? Speak up. That's why somehow you will get one more pi and that root pi will get cancelled. Check that out. Okay. So speak up. Gamma of n is equal to n minus 1 factorial if n is positive integer, isn't it? Speak up. Gamma of half is equal to, speak up, root 5. I hope you remember this, okay, while applying this, okay. So we don't know, I mean, how they design question. So that's why you better to remember including this one, okay. You better remember including, if they design, if they make the manipulation in the coefficient, what would you do, suppose, isn't it? Or if I design question, I'll do like that. Is that okay? Speak up. So that's why you remember this coefficient also, but never forget these things. Okay, this is very important. When you see old question, many questions can be solved like that. Okay, this is problem number 9.13. Okay, problem number 9.13. Okay, I think he used a relation between beta and gamma function. Okay, this looks like that. Okay, gamma of m plus n divided by gamma of m plus n, m plus m, like that. Something again, beta and gamma. Beta mn is written in terms of gamma, isn't it? Gamma of m plus. No, I don't remember like that. Okay, somehow the integral was converted into beta and then it is converted back to gamma integral. Okay, check this. I mean, you don't need a proof, but you need to note down and you should be able to apply it. Okay, speak up. That over. Now, these are the outcome of WKB method, which help us to find bound state energies. Okay, which help us to find bound state energy. Wait a second. I have one small exercise. Okay, you have this one. Am I right? This problem, I think I have done kx here, infinity here. Okay, I have taken trial wave function, variation principle. Okay, ax e power minus alpha x. Speak up. We solved. We estimated the ground state. Am I right? Speak up. We estimated the ground state. Okay, estimated. Now you know how to find energy eigenvalue, isn't it? In case of WKB method. Pick up. In case of WKB method, so you take the same problem, Kx. Speak up. You take the same problem, okay? You find En, you find E1, lowest energy. You just compare these two. We believe that this is more accurate, okay? We believe that this is more accurate, but here also we have done some approximation, okay? I will check that out, okay? Whether WKB method always gives accurate answer, or because we have done many approximations, okay? I mean, how do you say that this potential is slowly varying always, isn't it? Whatever I have done, it's not slowly varying, am I right? Speak up. But the assumption is potential varies very slowly, isn't it? Speak up. No, wave function we don't work out in WKB method. Yeah, energy eigenvalue. This gives energy eigenvalue, not wave function. But here we take trial wave function and we work out best estimated ground state. Am I right? You just compare these two. Which one is the lowest one? Check that out. Am I right? If this is the lowest one, this is more accurate. Am I right? Speak up. Can I say like this? Ground state. I mean, you find nth energy here, isn't it? In case of WKB method. So, but you find a ground state and you compare it with this one. This problem is done. I have shared one screenshot of the problem. Check that out. I think here it was written infinity. Okay, just replace it by alpha. Okay, that was a typing mistake. Speak up.
What is the essence of slowly varying potential?
No, I mean, actually, in Griffiths he mentioned like this, but while deriving, you need this one, d lambda of x by, or again, d by, I think, dx of 1 by p of x. If you put h bar by p, h by p is lambda. H by p is lambda. Am I right? It should be very much less than 1. But this situation will come actually. That is possible only when potential varying very slowly. That's why we have done that assumption. Am I right? While forming WKB solution. Okay. So, but in this case and all, it need not be. It depends on k. Am I right? The slope depends on k. If suppose k is higher, I mean, I don't know what is the error there. Okay, we need to check that out, or just see the book. You might have given somewhere. Okay, speak up. But again, that we don't know. I mean, which one is accurate? Am I right? Actually, in Jatili, he worked out many problems. The same problem you solved by different method. Okay, and again, and you compare them. Okay, let me mention those problems. Just remind me. Let me mention those problems. Okay, speak up.
So in practical situations, we can know how the potential is varying.
We know the potential.
Problems, we can only the best is we can assume. How will they mention that?
No, I mean, in exam question, they can't give any new question. Am I right? Speak up. That's why in exam question, in various situations, they will mention the potential, they will mention the trial wave function. You find the best estimation so that all of you get the same answer. They don't mention any new problem. But what kind of problem that can be solved, we know, isn't it? Speak up. But in the realistic case here, you need to guess the trial wave function. That is the actual thing. Or you need to take more and more parameters. Okay, variational parameter, and you need to work out. That is the actual thing. You need to work in 3 dimensions actually. Okay, we work only 1 or 2 problem on 3 dimensions, isn't it? So that is the actual case. We may need to, again, later they may apply the same thing for more than one. What do you call? Here we are studying only one particle system. Again, almost whole quantum mechanics, whatever we have studied, one particle system. Again, then multi-particle system. Is that okay? Speak up. So that's why. So again, that is extended. The idea is extended. Is that okay? There is one small topic I need to explain. That is helium 2 electron system. Okay. where we can find the ground state energy of helium using this WKB method. Okay, and I think hydrogen molecule or something. Both can be solved actually, but I didn't take up that one. No question as such. Hydrogen molecule ion and helium. You can estimate the ground state using variation principle. That is the actual application. Whatever the problem we did, I mean, this may have application, but usually that's one dimension problem, right? That is the actual application. If you go for helium, okay, so helium contains 2 electrons, am I right? Figure. With some assumption, we did that problem. But I need some identical particle chapter, okay, to discuss that one. Let us see that one. So, but WKB method, look at here. Again, we avoided differential equation. We found nth energy here, okay, not only ground state, okay. Here you can estimate ground state. After estimating ground state, you need to look for orthogonal wave function to this one. You have to estimate first exact state. It's quite difficult. But here we got nth energy. Most of the case, we need energy only. Is that okay? Speak up. But in some chemistry application, we need wave function also. So mod psi square gives the probability distribution. We can draw the structure of molecule and all if you know the probability distribution. Is that okay? So that's why we need best estimated wave function also, okay, in some application. Speak up. So can you compare these two? That's a very good exercise. Now, there is one more outcome of this WKB approximation, WKB solutions directly. You don't need any connection formula or something, okay? So that is, suppose if I have some, what you call potential. Suppose if I have some potential here. He has written potential in a different way, okay? But this can be applied to many different cases. Is that okay? Speak up. So I will take one, okay? I'll take one. I have potential like this. This is a barrier. It need not be symmetric, okay? Speak up. What is this one? Is a potential barrier, we say. Suppose if particle energy is less than this height of this, suppose this is V naught. If particle energy is less than the height of the barrier, okay, then classically particle cannot tunnel, am I right? Quantum mechanically is going to tunnel. We have seen it, isn't it? Suppose this is x1, this is x2, okay. The difference between this one and our bound state problem. So this region, look at here, this is classically forbidden region. There it was classically allowed region, am I right? Because in this kind of potential, if this is the energy, this was classically allowed region, am I right? That was bound state, this is scattering state, okay. Now here, this is classically allowed region, speak up, because energy is higher than the potential energy, isn't it? Classically allowed region. So this is classically allowed region, okay. This is classically forbidden region. Speak up. This is classically forbidden region. Now, again, the same WKB solution gives us the transmission coefficient, T. Transmission coefficient. If you know transmission coefficient, you know reflection coefficient. T plus R is equal to 1, isn't it? Speak up. So that is equal to e power minus 2 gamma. I'll write what is gamma is. Gamma is equal to 1 by h bar integral x1 to x2 mod of p of x into dx. Why I have written mod? Now the region x1 to x2 is classically forbidden region. Here you need to integrate in the classically forbidden region. I will remember like that. That bound state problem, we need to integrate in the classically allowed region. This is scattering state problem, transmission coefficient, so tunneling problem. Okay, you need to integrate in the classically forbidden region, x1 to x2. Is that okay? Speak up. Mod of p of x is equal to root of 2m, okay, v of x minus e. Is that okay? Why we put mod to differentiate it from momentum? This is not actually momentum, right? Because in classically forbidden region, we don't define velocity or momentum. Your kinetic energy is negative in classically forbidden region. That's why he put mod to differentiate it from momentum, which is defined in the classically allowed region. Okay, speaker. it will give us transmission coefficient. This is also another outcome of WKB solutions. Speak up. Now look at here. Again, I observed one thing there, okay? Again. So this is the potential that he has given, okay? Some barrier, okay? 0 here, A here, okay? Speak up. I mean, just do it, okay? Energy is like this. This is the energy. Is that okay? He plotted wave function. I will have a separate class on this one, okay? What is mod of P of x? That's equal to root of 2m V of x minus e. Maybe while revising, we shall have one separate class plotting the potential and plotting the corresponding wave function. That okay? Rough wave function. Okay, it need not, but it should follow all of the properties, all of the logic and all. Okay, if you plot what you call wave function, qualitative structure of wave function. Okay, speaker. It will be sinusoidal here. I'm right. Free particle here. Okay, I have taken one barrier of some other shape. Pick up. If this barrier, this height is constant here, we know the solution. I'm right. Some sine hyperbolic function or something. I mean, we have a note on this one in the second chapter. Pick up. Speak up. That we know. Suppose if it is variable, you have to go with WKB solution. Is that okay? Speak up. You need to integrate that one in that region. Okay. If it is constant, we can apply our what we call continuity of the wave function, continuity of the derivative of the wave function. We can work out the reflection and transmission coefficient. But that problem was very lengthy. I skipped it. Okay, speak up. So 0 here, A here. Is that okay? So if our wave function is like this, okay, so then it's going to decay here. Suppose if you have some wavelength here, okay, so you will have the same wavelength here. I don't know whether, no, these distances are not same. You will have the same wavelength, but your amplitude will be decreased. Why? Speak up. Because some particles are, again, amplitude. Do you remember amplitude will talk about probability current density? Our probability current density is for e power I kx, a e power I kx. When we found probability current density, it was mod a square into, I think, h bar k by m. Check that out. When we found probability current density, okay? Speak up. I mean, this A is nothing but what you call amplitude of the wave, okay? Speak up. Amplitude of this wave should decrease because some part is reflected here, okay? Speak up. Quite classical idea here. You can draw your wave function like this. Everywhere you should make the curve smooth because there is no infinity here. Potential is not touching infinity here, okay? Curve is smooth everywhere. Speak up. Just right. I just found in the Griffiths book again. You should know this one because look at here. What is k here? Root of 2m e by h bar. That's equal to 2 pi by lambda. What is k in this region? Again, the root of 2m e by h bar is equal to 2 pi by lambda. Remember that lambda de Broglie wavelength. If you think of, okay, that is the same in this region and in this region. In both region, energies are the same. Am I right? Because your k value is same. But here it is exponential solution. Am I right? In classically forbidden region, our Schrodinger equation solution is exponential. We make it exponentially decaying solution. That is actually physically what you call realizable. Am I right? When you shoot the particle from here, if suppose this region is wider, you will have less transmission coefficient. Am I right? You will have less probability, or you will have less amplitude of the wave there. Okay, that's why you it should be exponentially decaying solution here. Okay, that is the idea. But actually, general solution is linear combination of exponentially increasing and decreasing solution. Am I right? We write e power plus kappa plus or minus kappa x. Am I right? That's how we write the solution. Okay, speak up. Shall I move on? Yeah. Just draw this one also. Now I'm going to apply this what you call this part of our WKB outcome, that is transmission coefficient, to one realistic problem, alpha decay. Alpha decay. That is example number 9.2. Example number 9.2 in Griffiths. Okay, Gamo's theory of alpha decay. Gamo's theory of alpha decay. The basic idea here is I will make it brief, okay, because not much questions designed on this one, okay, but this what you call very historical what you call fact actually, Gamo's theory. Again, you have a nucleus which is believed to be of shape sphere, okay, spherical one, okay, and your alpha particle is ejected here. Once alpha particle is ejected, whatever the rest of the nucleus, okay, I will call it as a daughter nucleus. We say like this, okay. I will take that daughter nucleus, charge is plus z into e, and alpha particle is ejected from that one. I will consider this is alpha particle, which contains what is the structure of alpha particle? Helium nucleus, 2 proton, 2 neutron. Am I right? What is the charge? Plus 2 times electron charge. Am I right? Pick up. Is that okay? Once alpha particle is ejected, I will take the charge of this what do you call daughter nucleus as plus z into e, okay, and charge of this alpha particle is 2 into e, okay. When alpha particle, which contains 2 proton, 2 neutron, when it was inside the nucleus, this is nucleus, okay, speak up. When alpha particle was inside the nucleus, okay, it was what you call experiencing attractive nuclear force. Am I right? Speak up. I mean nucleon reaction, isn't it? Nucleon interaction. Am I right? That is attractive in nature. Am I right? Proton, strong nuclear force. Is that okay? Proton, 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 neutron, neutron, neutron. They are all bound by strong nuclear force. Am I right? When this alpha particle was inside, it was experiencing strong nuclear force. Okay, it was experiencing attractive force. Can I say like this? But once alpha particle goes out of this nucleus, this is a nucleus. Okay, once alpha particle just leaves the surface of the nucleus, if I believe, okay, pick up. Suppose this r is the radius of the nucleus. Is that okay? Pick up. Once alpha particle leaves that one, it will this what you call this interaction is Coulombic now. Is that okay? And it is a repulsive in nature. Is that okay? So with that idea, look at here. Our idea is alpha particle is pre-found inside the nucleus. Okay, speak up. Alpha particle was there inside the nucleus, and it was experiencing some attractive force, and it is trying to come out. Okay, it's going to tunnel and it will come out. Once it comes out, it will experience what you call your repulsive, what you call Coulombic interaction. Okay, again, this whole problem is a kind of spherical symmetry problem. Is that okay? Speak up. We work with spherical polar coordinate. Okay, so that's why we draw, look at here, potential as a function of r. We draw potential as a function of r. Wait a second here. Is that okay? Now, so I will take it as 0. I will take it this point as a radius of the nucleus. Okay, he has taken r1. Let me take r1 only. Okay, r1 is the radius of the nucleus. Is that okay? R1 is the radius of the nucleus. Okay. Whatever we are studying alpha particle. What are the forces? What are the potential which is experienced by alpha particle? Okay. Inside that one, radially, you have to think radial. Okay. From 0 to R1. Okay. From 0 to R1, it was experiencing some attractive potential. Am I right? We don't know what exactly that potential is. Okay. Speak up. But it is attractive. That's what we know. Am I right? Speak up. I'll just write it as minus V naught. Pick up. R1 is the radius of the nucleus. Okay. We are studying alpha particle. Potential felt by alpha particle. Is that okay? Pick up. Alpha particle is preformed inside the nucleus and it was experiencing some attractive strong nuclear force inside that one. Okay. Once it comes outside, it will experience, pick up. What is the so Coulombic what do you call interaction? Pick up. Plus ZE into 2 times E divided by 4 pi epsilon naught into R 1 by R. Am I right? Pick up. Pick up. This is a radial distance. Okay. This is a radial distance from the center of the nucleus. I'll say like this. Speak up. Within the nucleus, okay, it was experiencing what you call attractive potential. I mean attractive force. That's why negative potential. Okay. Outside that one, potential is positive means it's a repulsive what you call force. Can I say like this? Pick up. So now this is equal to V of R is equal. That's equal to Z 2Z E square divided by 4 pi epsilon naught into 1 pi R. Is that okay? Speak up. No, we don't know. We don't know. That is, again, there are many models over there, okay? Shell model and all. But still, we work out the shell model for, what you call, individual nucleons, am I right? Not for alpha particle, actually, isn't it? But we know that it is attractive. We know that it is attractive. So check that out, okay? I mean, in nuclear physics, there may be some idea, okay? But it doesn't matter, okay? It doesn't matter for us, okay? But it is some attractive potential that we know, okay? So now, whatever the alpha particle which is coming out, actually, this diagram is not so appropriate, okay? I will redraw later, okay? I will redraw later. Whatever the alpha particle energy, whatever we get here, okay, that is actually so low. That okay? This is the energy of the alpha particle. Whatever alpha particle is coming out here, that energy is so low. That is very, very lower than this height of this barrier. This is a barrier. Can you see here? Speak up. Suppose alpha particle is here, okay? It is experiencing some negative potential. It has some energy E, positive energy, okay? So now when it comes out, okay, it has I mean, compared to this height, you can measure the alpha particle energy, am I right? When it comes out, that energy is like this, okay? Now this is R1, I will call this one as R2. These are classically forbidden region. Speak up. It's definitely a tunneling process, am I right? Speak up. Because, I mean, you can't say what is happening inside the nucleus. But when we see from here, you got alpha particle energy is like this, but our potential curve is like this. Speak up. Height of this potential curve is what you call very, very higher than the energy of the alpha particle, isn't it? Speak up. Inside that one, it should be what you call some attractive potential. Am I right? Then the problem is a quantum mechanical tunnel. Decreasing, yeah, that's right. No, Coulombic interaction R 1 by R dependency. 1 by R dependency. Speak up. Force. Electrostatic force, am I right? That will decrease. This will talk about electrostatic force or potential, okay? Speak up. But I'm talking about whatever you get outside, that is alpha particle, am I right? Which has some energy. Is that okay? Which has some energy, which has some for a given nucleus, I think that energy is constant. We shall see that one. Plots and all. Is that okay? And the process should be quantum mechanical tunneling. How do you find this R1 is a radius of the nucleus. Okay, I mean we have models for finding the radius of the nucleus. Okay, R2 is how do you find this R2? By equating E to this one. Speak up. If you equate E to 2Z E square divided by 4 pi epsilon naught 1 by R2. So can I write like this? From this one you can get R2. R1 is the radius of the nucleus. Okay, because you need that one. Am I right? Speak up. Then e power minus 2 gamma, that is your transmission coefficient, okay? Speak up. E power e power minus 2 gamma, okay, that is your transmission coefficient, am I right? What is gamma here? So gamma in this case 1 by h bar integral r1 to r2, integral r1 to r2, okay, root of 2m v minus e, that's equal to 2z e square divided by 4 pi epsilon naught 1 by r minus e, that okay, dr. I'll not work out this one, okay, I'll not work because it will be very time consuming. We don't need that one, okay, this integral. But in Griffiths he gave all substitution and all to work out the integral, okay, speak up. Ultimately, what you will get here is that okay? Speak up. I'll write this gamma directly. R2 you can find it from here. R1 is a radius of the nucleus. Yeah, he kept R1 as it is because the radius of the nucleus is different for different nucleus, isn't it? So let me write gamma directly. Is that okay? And e power minus 2 gamma is the transmission coefficient. That gamma is equal to, look at here, K1 into Z divided by root of energy of the alpha particle, whatever you got, minus K2 into, okay, root of Z R1. R1 is the radius of the nucleus, okay. Z is atomic number. And he has given this K1 and K2 value. Those are universal constant. Your H bar, whatever comes, okay. Pick up mass of the 2m is mass of the alpha particle here. Is that okay? Pick up mass of the alpha particle, which are universal constant, okay. So let me write this K1 and K2 here. K1, that's equal to, he evaluated that one, that's equal to, I think, E square by 4 pi epsilon naught or something. I'll not write that one, okay? Just note down from the book. 1.98 mega electron volt power half. Okay, K2 is equal to, because this gamma e power minus 2 gamma, this gamma should be dimensionless. Okay, speak up. This gamma should be dimensionless, then K1 should be of the dimension of root of energy. That's why mega electron volt power half. Is that okay? Speak up. K2 is equal to 1.485 Fermi, 1.485, wait a second, per Fermi, per root Fermi, because you have root of radius. Radius is usually measured in terms of Fermi, isn't it? So minus half, can I say like this? Pick up Fermi power minus half per root of Fermi. Am I right? Because this is in terms of root of Fermi, isn't it? Pick up. Now transmission coefficient is equal to e power minus 2 gamma. Okay. Wait a second. I'll come to that one. I'll come to that. These are the outcomes. Okay. E is the energy of the alpha particle. Z is the atomic number of daughter nucleus. Okay. I've taken daughter nucleus. Z is the atomic number of daughter nucleus. Okay. R1 is the radius of the nucleus. Is that okay? Speak up. Now look at it. I mean, the radius of the parent and daughter nucleus is not much different, isn't it? Pick up. Yeah. Now look at here. I will have one assumption here. Okay. My nucleus is of spherical in shape. Okay. Its diameter is 2r1. My alpha particle was what you call trying to come out. It was hitting the walls of the nucleus. I'll say like this. It was experiencing some attractive potential, but it is hitting the walls. Okay. Pick up. So I mean the average velocity of this alpha particle. Wait a second. The average speed of alpha particle, average velocity of average speed of alpha particle, I will take it as v. Speak up. I'll take v as average speed of alpha particle inside nucleus. Is that okay? Inside the nucleus. Pick up. Now, can I write that speed as diameter by time taken to reach from one corner to other corner? Can I say like this? Suppose if it is taking some time t naught to reach from one corner to other corner, okay? Distance by time. Diameter by time, I'll write t naught. Is that okay? Pick up. Diameter is nothing but 2r1 divided by t naught. Pick up. Now I'll solve it for t naught. T naught is equal to 2r1 whole divided by, pick up, speed of alpha particle. Speed of alpha particle. What is this one? This is time that it takes for one collision. Can I say like this? One collision. Suppose if it starts its journey from here, if it hits the wall in the other corner, is that okay? This is the time that it takes to make one collision to the wall. So can I say like this? Speak up. So that's why frequency of collision I can write like this. Okay, how many collision it can make per second? Okay, look at it. Frequency of collision. Frequency of collision, that's equal to 1 by t naught, that's equal to v by 2r1. Isn't it? So can I say like this? Frequency of how many times it is colliding the wall of the nucleus per time. Okay, pick up. This many times it is colliding per time. Is that okay? Frequency of the collision. Now, why I need this one? Because this transmission coefficient can be written as transmission probability also. Is that okay? That's a probability actually, right? It is less than 1. Now, this is a probability for one trial actually. Just like when you toss the coin, what do you mean by half? When you toss the coin once, okay, probability of getting head is half, am I right? Tail is half, like that you say, isn't it? Figure. To verify that one, you need millions of trials and all. But look at here, alpha particle is not only doing one trial. You are not. It's not like you are not tossing only once and talking about probability. Okay, it is doing a lot of trials actually. Then that probability should be multiplied. Am I right? For each of the trial, you have what you call this much probability that it will come out. This is a probability that it will come out. Am I right? Transmission coefficient. This is nothing but probability that alpha particle comes out of the nucleus. Okay, pick up for one trial, but it is making this many trials per time. For each and every trial, this is the probability of coming out. That's why total probability that it comes out per time, okay, that should be this one multiplied with this one. Pick up. Are you getting point? No, I will take it up. Okay, I will take it up. Now, what I'm going to do is probability of emission per time. Can I say like this? Probability of emission per time. Okay, that's equal to multiplication of frequency of collision inside or number of trial per time multiplied with probability of each trial. Can I say like this? Probability of each trial, like this one. I mean, I think you may able to understand this one in probability theory. Basic probability theory we shall do in the beginning of statistical physics. Is that okay? Speak. Probability of emission per time, okay, that's equal to, look at here, V by 2R1 multiplied with, okay, e power minus 2 gamma. Is that okay? Probability of emission per time. It is doing this many trials. Each trial have got this many trial per time. Each trial have got, this is the probability. Each trial have got, this is the, each trial have got probability, this much amount. Okay, that should be multiplied. This is actually basic probability theory. Now look at here. Now this quantity, probability of emission per time, okay, that is inversely proportional to lifetime of the nucleus. Can I say like this? Or half-life of the nucleus? He defines lifetime actually. Lifetime may be different from half-life. Okay, I don't know what is lifetime. but lifetime is proportional to half-life. That's what I can say. Is that okay? Speak up. Now, if there is more probability of emission, okay, then lifetime will be low, isn't it? Lifetime of the nucleus will be low. Parent nucleus will be low, isn't it? Speak up. If there is less probability of emission per time, okay, it will live for long time, isn't it? That's why this should be inversely proportional to lifetime of the nucleus, okay? Inversely proportional to 1 by, I'll write tau, or yeah, tau, or half-life also. You can take half-life also. Half-life is called as lifetime? I don't know. I don't remember. Speak up, anyone? Can you hear me on Google Meet? He didn't mention, I think, clearly. Just check that out. Yeah, no. Half-life, okay? So, no, I'll take lifetime also. Tau, okay? So, by tau is lifetime, okay? Half-life is equal to lifetime into log of 2. Okay, we shall see this one in the nuclear physics. Tau is the lifetime of the nucleus, okay? This is inversely proportional to lifetime of the nucleus. I'll rub it out, I don't need. This is inversely related to lifetime of the nucleus. So this is per time actually. You can just equate. You don't have to worry about the proportionality factor actually. So that's why what I can do here is this lifetime is nothing but reciprocal of this one, 2r1 by v into e power plus 2 gamma. Check this out. Gamma is this one. That okay? And half-life is nothing but this is half-life. Practically, we measure this one, am I right? Half-life of the nucleus. Half-life is equal to, pick up, log 2 times this one, okay, log 2, okay, multiplied with 2r1 by v into e power 2 gamma. Am I right? Speak up. You can take some constant. I think he equated actually. Is about, he has written is about, not is equal to, okay? It doesn't matter. If any constant comes, I mean, you can show the results, okay? You can show the curves, okay? If any more constant comes here, you apply log and plot actually, am I right? You need gamma. It is e power gamma, am I right? That's gamma contains energy term, isn't it? You need to apply one more log. That will be some y-intercept actually, okay? Speak up. Now you take log of this one, log of 2 half, okay? That's equal to, can I write this as some log of constant plus 2 times gamma? This whole thing is constant. That's what I'm talking about. Or I'll write 2 times what is gamma? K1 z by root t, okay? Minus K2 root z r1, okay? Plus some log of c. Whatever constant you are talking about, you absorb it here. And we plot this one versus this one, okay? Speak up. Now, when we plot that one for different nucleus, definitely I can, I mean, when I plot it versus 1 by root t, and we will take 1 by root t increasing in this direction, okay? Speak up. 1 by root t increasing in this direction, log of half-life, usually in years actually. Half-life, I mean, for the thorium and uranium, whatever he has taken, that is in terms of years. Isotopes means Z value same, am I right? Speak up. Isotope means Z value same, am I right? If Z value same, this should be the same, am I right? Speak up. For uranium and uranium isotope, you will get one straight line. It is increasing in this direction, okay? 1 by root t. When you plot this one versus 1 by root t, it should be straight line with positive slope. Okay, but we have taken 1 by root t increasing this direction. That's why it is looking like negative slope. Is it okay? Speak up. Why we don't plot it like this? Because uh, if you plot 1 by root t like this, the increasing in this direction, what is 0? 0 means infinite energy. That's not comfortable to write. Are you getting it? That's why whenever we plot with 1 by something, okay, we make it like this. It is increasing in this direction, okay, so that we avoid that infinity factor. Speak up. That's perfectly straight line, and you can have experimental what you call points here. You can calculate the slope, and you can compare it with this one. 2 into k1. K1 is written here. Speak up. Z is the Z value of that particular nucleus. Now, if you change the nucleus, what will happen? These terms will change. Am I right? I have plotted this one versus 1 by root t. Am I right? Speak up. For different Z and different Z means different R also, radius of the nucleus, isn't it? So this y intercept will change. Again, you will have different curve, but slope is the same. You plot the same slope, but Z into K1, am I right? That should decide the slope. Huh?
Sir, for this case, the slope is positive, na?
Huh. No. That's what I'm saying. Slope is positive if you plot 1 by root t increasing in this direction. But you have plotted 1 by root t increasing in this direction. Okay. I mean, that's what practically they plot actually. Okay. Just see the curve. So now I think if I change Z, slope should change. Am I right? Because he didn't show that one. Or I don't know. He will take Z by root t. Okay. He didn't mention that one. But look at here, whatever the, again, this curve, if suppose if it is for urium and its isotopes, okay, speak up. Now, again, from practical curve, you can find its slope. You can compare it with Z K1 into 2. That will have exact match actually. Is that okay? Now, whatever we derive in the theory, okay, that will have exact match in the experimental outcome. So this was very old quantum theory, this WKB method. This is what you called as first victory of quantum mechanics, okay, which explained experimental aspect so well actually. I don't know exactly how much accuracy we got, this slope and whatever the quantity here. I think we need to check out some nuclear physics book, okay. Not parallel, because I mean, I think they might have plotted Z by root t. Okay, he didn't mention properly. If you plot Z by root t, definitely it will be parallel because slope should be the same. Am I right? Pick up. If you are plotting 1 by root t, definitely it will be not parallel because Z is the factor which decides the slope, isn't it? R1 decides definitely, but this will be y intercept. Y intercept is changing. That's what I'm saying. Okay, Z is saying R1 is changing. Pick up. So you better to plot Z by root t. That's a better idea. Okay, Z by root t. No. These are all universal constant. Z will No. Look at here. Again, you are uh, for a given nucleus, for a given isotope, this Z is constant. Am I right? Pick up. And radius is constant. Okay, we are plotting for given nucleus. Let me change the slope actually because 1 by root t. Z is the factor of the slope. Okay, but again, this is for thorium and its isotopes. Suppose y intercept would be different only. In that okay, speak up. But I think you should plot Z by root t. I mean, I don't know practically what they plot here. Is that okay? But whatever the slope, whatever you get here, that will exactly match up with this one. Is that okay? This expression. Is that okay? Speak. Yeah, I think we better to close the session. Just check this out. Example 9.2. I mean, you don't have to work out those integrals. Okay, you can skip that one. Yeah, that completes this WKB method. Okay. Speak up.
We are taking long hours.
No, again, this was e power 2 gamma, am I right? How to plot it? It would be quite difficult to plot and verify the coefficients and all. This is a straight line, am I right? We always do that one experimental because straight line slope you can quickly calculate, am I right? I mean, now if you plot this toe half versus this one, you will have some curvature. And how do you verify whether it is the same curvature? Am I right? Once you have a straight line, practically you can quickly find the slope and compare the expressions, isn't it? That's why whenever we have a curvature, I mean, if it is possible, we try to convert it into straight line. So that we can verify the coefficient, whatever comes in the expression. Is that okay, speaker? Yeah. So next topic is scattering theory. What shall I do? Shall I start in evening? Because I want old batch student to be there in the scattering theory. We shall do one thing. We shall discuss MCQs in the next session. Is that okay? Huh? Ring problem. Yeah, that's very good. We shall discuss a ring problem. Okay, ring problem and that perturbation problem. We shall discuss that one in the next session. And evening we shall start scattering theory. I think I need 2 big sessions to complete scattering theory. It's also very lengthy mathematics, but we shall take mathematical outcome directly. We shall try to grab as much. Born approximation problems are quite straightforward. I'm going to say, okay, not easy because some integrals are quite challenging there, okay, but straightforward. Problems are straightforward, but there are some questions on that partial wave analysis and all frequent questions actually we have to discuss, but it needs, as I told yesterday, spherical Bessel function, spherical Newman function. I will take it directly. Okay, he also do like that only, isn't it? In the you have seen in the 4th chapter, right? He will write the differential equation. He will write the solution is associated legendary function, and that is related to associated legendary polynomial and all. Okay, he don't solve it. Okay, I mean for physics discussion, we don't need complete solution, the mathematical solution, but we need the properties actually. What happens when you go to infinity or some boundary condition? These things we need. Okay, yeah, we'll see that one. We'll meet at 8:05. We shall discuss some problems. Okay, yeah. In the evening, we shall continue with scattering theory.